Welcome to the VR session. There will be 4 papers, is that right? Yeah. And and again, just to remind you, it's each speaker will speak for 20 minutes, and then there'll be a 5-minute Q&A. So the first presentation is called VR Splat, Fast and Robust Gaussian Splatting for Virtual Reality.
Thank you. My name is Xuechang Tu. I'm an undergraduate from China, and I will present our work, VR Splat, Fast and Robust Gaussian Splatting for Virtual Reality. This is a joint work with my awesome colleagues, Lucas, Michael, Bernard, and others. Let's first take a look at our results. On the left is 3D Gaussian splatting directly applied to VR setting. And you can see that there are several severe visual artifacts. And our method removes almost all of the quality issues. So virtual reality is a natural use case for novel visual synthesis. You can easily capture the reality and re-experience it immersively in virtual reality. And also, I know there are some papers that aims to provide a designing interface, allow users to use their hands to intuitively design objects using 3D Gaussian splatting. Also, I think maybe future games may utilize novel visual synthesis. And 3D Gaussian splatting has emerged as an exceptional novel visual synthesis method. It provides very good performance, and its point cloud-like representation is easy to manipulate. However, there are several challenges directly applying 3D Gaussian splatting to VR. The first is visual artifacts. There mainly are two visual artifacts. The first one is popping, and the second one is projection error. We'll talk about them later. And the second challenge is the stringent demands of VR. A smooth VR experience requires about above 72 frames per second and very high resolution. Let's go through the basics of 3D Gaussian splatting. So it represents scenes as a set of 3D Gaussians. Each Gaussian has a position, opacity, and anisotropic covariance for its shape, and spherical harmonic coefficients for its view-dependent color. And given the set of 3D Gaussians, the rendering procedure is as follows. We shoot a ray from the camera through each pixel and calculate the color and opacity of each Gaussian along this ray, and blend them together using alpha blending. And we can calculate, the whole process is differentiable. So we can calculate a loss between the rendered color and the ground truth image, and use backpropagation to optimize the parameter of 3D Gaussians. But our paper focuses on the rendering process, not the training part. Several approximations are made in 3D Gaussian splatting rendering to accelerate the rasterization. The first one is that, for example, here are two Gaussians. 3D Gaussian splatting blends the Gaussians according to their view space depth from near to far. So in this case, the blue Gaussian will be rendered in front of the green Gaussian. And this is incorrect in their overlapping region. And this leads to a problem that when you move your camera or rotate your camera, the Gaussians, their view space depths may change, and the ordering of Gaussians may suddenly change. And this results in some sudden color changes in in the rendering image. In VR, you have constant head movement. So this popping artifact is particularly annoying in VR. And the second approximation is that 3D Gaussian splatting, before rendering the Gaussians, they first project each Gaussian to the image plane to get a 2D geometry. But directly projecting a 3D Gaussian to a 2D plane does not yield 2D Gaussians. It uses an approximation to for faster rasterization. But when the Gaussian is further away from the camera center, the projection error is larger. So in VR, we have large field of view. So this projection error is also particularly obvious in VR. Let's talk about these two problems respectively. So this video shows that shows the popping artifacts. You can see the sudden color changes on the table, and the paper Stop Pop proposed an elegant solution to this issue. Let's start from the simple solution. We can perform a per pixel full sort to the Gaussians. That means for each pixel, we shoot a ray from the camera through this pixel. And then we sort all the Gaussians according to their depths along this ray instead of their view space distance. And this way, we get view consistent results, but sort all the Gaussians along all the rays are too slow. And Stop Pop proposed a hierarchical sort strategy. For time reasons, I'm not going deep into this, but it's not perfect theoretically, but I personally think it's I don't spot any remaining artifacts in practice, but it's still slower than the original 3D Gaussian splatting. For the second quality issue, it's demonstrated in this video. You can see there are a large black Gaussians floating in front of the camera. And this is caused by the inaccurate projection approximation. And the paper Optimum Projection proposed to solve this issue by projecting each Gaussian to their individual optimal plane to minimize their projection error. So previously, all the Gaussians are projected onto the same image plane of the camera. And now they are projected onto different planes, and the error is much smaller. And we can still slightly modify the original rasterization pipeline to make it work with the new representation. But it still produces additional computation, so it's slower. And then we show a full comparison of 3D Gaussian splatting and our method integrating the two quality solutions mentioned before. So now all the visual artifacts are gone. Let's talk about performance. Smooth VR experience requires about 72 frames per second, but current hardware can achieve this. So maybe an RTX 9090 can solve this problem forever, but there are still many optimizations can be done. So the first one is that an important optimization in Stop Pop is not directly compatible with optimal projection. In Stop Pop, a Gaussian tile combination is pruned if the maximum opacity contribution of the Gaussian inside this tile is less than a threshold. That means the Gaussians are almost invisible inside this tile. So with optimal projection, we project the Gaussian to its optimal plane instead of the common view plane. And our tile is in the view space. So we propose to project also project the view space tile to the optimal plane, and this yields a quadrilateral. So we can still efficiently compute the maximum contribution point of the Gaussian inside this quadrilateral. And this optimization speeds up the rendering for about 50%. And CD Gaussian splatting uses a heuristic-driven densification, and it produces redundant Gaussians. And a high number of Gaussians impact both performance and model size, also the memory consumption. A mini-splatting reduces Gaussian number for about 3 to 10 times with comparable quality to CD Gaussian splatting. So we propose to fine-tune a mini-splatting model with our new rasterization without densification to retain the benefits of both mini-splatting and our quality upgrades. Directly render a mini-splatting model with our new rasterization will cause quality degradations. So the fine-tuning process recovers the quality quickly. And we find that about 5,000 steps is appropriate. And this fine-tuning approach is compatible with any baseline as long as its output is in the 3D Gaussian splatting format. To further accelerate our rendering process, we utilize a common technique in VR, the foveated rendering. We implemented fixed foveated rendering, and we consider it a good trade-off between quality and performance. And it can be easily extended to dynamic foveated rendering as long as eye tracking devices are available. So a naive foveated rendering solution requires 2 rendering paths. First, we render a high resolution near the center of the image, and we render a low resolution. In this case, we render it with a half resolution in each dimension. And we blend them together using a linear weights, and we get the final smooth image. However, render the same scene twice requires to process the same set of Gaussians twice, and this yields redundant computation. So we further propose to use a single pass foveated rendering. We split image into tiles of size 16 by 16 and 32 by 32. The middle of this image has small tiles, and the periphery of this image has large tiles. And we launch a single CUDA kernel, and each thread block inside the kernel handles a tile in a similar manner. So each tile we sample, for each tile, we sample 16 times 16 pixels inside it. For the high resolution part, that is our small tiles, 16 by 16 tiles, we essentially retain the original resolution. And for the large tiles, we in effect half the resolution. And we also blend them together to get a smooth transition. And this technique can be applied to further resolution reductions. We only implement it for this 2-level foveated rendering. And we carefully implemented this technique to gain maximum speed. We also utilize a visibility mask. In some for almost all of the headsets, some regions of the image, the rectangle image, are not visible inside the headset. Those contents are only used when our frame rate is low, and we use a frame extrapolation to generate new frames. So ideally, we can skip the rendering of this invisible region and does not impact the quality. But this requires some additional processing. So in pre-processing of 3D Gaussian splatting, we need to calculate the number of tiles inside a rectangle. Now with visibility mask, we need to calculate the visible tiles inside a rectangle. So we pre-calculate a sum area table. And with this table, we only need full access to calculate the visible tiles inside the rectangle. And visibility mask reduces about 11% of tiles and 6% of Gaussian tile combinations. And finally, we present our performance of an RTX 4090 at about 2K times 2K times 2i resolution. You can see here, 3D Gaussian splatting actually is good in terms of performance, but it has severe visual artifacts. And mini splatting suffers from the same problem, but it still accelerates the rendering process. With stopped pop and optimal projection integrated, resolves almost all of the visual artifacts, but the performance is much worse. And by comparing the last two lines, our 2-pass foveated rendering and our final method, 1-pass foveated rendering, we can see that we indeed reduce much redundant computation, and we achieve less than 13 milliseconds per frame. That is above 72 frames per second. And for some data sets, we even achieve higher than 100 frames per second. And we conduct a user study to verify our finding. This is because static image metrics do not reflect temporal inconsistencies such as the popping artifacts, which is obvious when you move your head. And also the metrics require ground truth, while the ground truth is unavailable for our large field of view VR images. And the details of the user study is presented in our paper. We recruited 25 participants, and we find that our method is preferred against mini splatting. So in conclusion, our method may be the first to achieve artifact-free and real-time novel biosynthesis in VR. And we release our code in our web page, project page. You can, if you are interested, you can scan this QR code and try this yourself. Thank you.
Great. Are there any questions? Go ahead.
Hi. I realize this isn't the intended purpose, but I was wondering if these same techniques could be applied to applications outside of VR. For example, the interpolation of already existing live action footage in order to increase the frame rate, or if that would be a complete misuse of the.
So some techniques are available in normal setting. So the foveated rendering technique and our visibility mask optimization are limited to VR. But in normal field of view and normal camera settings, the both popping artifacts and the projection error are not very obvious.
Thank you.
Are there any other questions? I have a question. This is really impressive.
Thank you.
And what if you kept up with doing the next step of optimization? What would you do next? Do you think you've completely, it's done? There's nothing else to do? Is this as good as it can get?
No, I think currently our method still requires a top PC hardware to run smoothly, and this can certainly be have room for optimization. But I think I have only one idea for further optimization. That is utilizing eye tracking device, and with eye tracking we can dramatically reduce our samples to make this image clear.
Right, using foveated rendering for actual foveated vision.
Yeah.
Yes. All right. Any other questions? Oh, yes. I think they're going to bring you. Oh, sorry. There you go. Yeah, bring you a mic.
Thank you. Thank you for the presentation. And maybe I'm not super familiar with the foveated part. So, is it like any special design for which part you decided this part should be fine resolution and the other part should be low resolution, or just the center?
So in VR, the camera center is not at the image center. We actually we choose the camera center, and we choose the region with half width and half height as the high resolution region, and the rest region are the low resolution region, and we render it with half resolution at both dimensions.
So this is basically like a fixed according to camera or according to the images. I'm just curious about like when I'm using the VR and I'm not moving my head and I'm just moving my eyeball, like looking someone, that will be like.
Sometimes it's visible when you only move your eyeball.
Okay.
Yeah,
That will be a little bit blur, right? I'm just
yeah,
curious.
but I think in most use cases, people are more inclined to move their head instead of eyeball.
And as another for the result part, and I noticed that there's a results in the MIP 360. Do you have any special reason like for this data set and your method is not working like as fast as the traditional CDGS? Any special reason for this data set? Like show in your table. I guess the timing is.
I think this is because these scenes are complicated, and 3D Gaussian splatting, actually you can see that mini splatting is not performed well on these two data sets either. So I think this is because mini splatting does not yield as much as yield the number of Gaussian reduction as much as the other two data sets.
Okay, so in this data set, I mean that the total number of the Gaussians is much more higher than the other two data sets.
Yeah.
So that'll make it difficult. Okay, that's reasonable. Thank you so much.
Are there any methods for converting from the 3D Gaussian space to like a more traditional 3D space or file type such as like STL, DXF, or like polygonal ones like representing it in triangles? Is there any like conversion method between that, or does it stay firmly in the Gaussian space just for time reasons, or are there methods for that?
3D Gaussian splatting is achieves both the best performance and quality. So we choose this as our start point.
It was more for if you wanted like to scan an item, say, and then save its dimensions on a more basic level. I was more. I know it's not used. It was more of just is that method available if the user so chooses.
Sorry, I don't get.
I think that's a great topic for conversation, but it's a different topic, so we should probably take that one offline.
Sure.
All right. Thank you.
Thank you.
Okay, so the next paper is entitled Enhancing the Precision of a User's Hand When Sliding on Objects in VR.
Hello, everyone, and thank you for being here. I'm Anna Kozłowska, and on behalf of my team of my co-authors, Mikołaj Wójcik, Maciej Spychała, Joanna Porter-Sobieraj, and Jakub Ciecierski, I'm excited to be able to present you the research on enhancing the precision of the user's hand when sliding on objects in virtual reality.
In this talk, I'll walk you through why improving hand precision in VR matters, how we approach the problem, and what we found out in our user study. Our goal was to address a specific issue in virtual reality. When users interact with virtual objects by sliding their hands over them, precision often drops due to the lack of tactile feedback. As a result of our research, we propose a purely software-based solution that enhances this kind of interaction without the need for any additional hardware. But first of all, let me give you a brief overview of hand interactions in virtual reality. Typically, when we talk about the interaction, we imagine classic desktop or mobile applications and user interfaces to interact with them. Even in 3D applications, we have to use mouse or keyboard, and we have to perform interaction through intermediate 2D screen. However, interactions in VR applications differ a lot from the desktop ones, as they can omit intermediate 3D space to two-dimensional screen transformation. They allow users to interact with the virtual environments in ways never met before, as the user's hands, that means also the controllers, are moving directly in 3D space. This new problem assumptions require specialized human-computer interfaces. Currently, we have several commonly used interaction techniques in virtual reality. One is a combination of raycasting as a selection mechanism, then pulling selected objects into the user's hand. Another widely used technique is a combination of proximity-based selection, then attaching the object to the hand through the predefined sockets. And lastly, we have a large group of the interactions that are based purely on the physics. In this research, we focused on the physically based interactions. In this category, we can distinguish three distinct types of interactions: pushing, grabbing, and running a hand over object. How those three interactions differ from one another? In the first two, the object on which the interaction is performed is perceived as movable, so it's either small or its mass cannot be too big. The third category assumes that the object is either huge or immovable, so physically speaking, its mass is much higher than the maximum mass of the object the human can move. Our research is handling the problems that occur only in the last physically based interaction, that is, during sliding over the stationary object's surface. To be able to address the problem, we have to comprehend how the final position of the hand is calculated in virtual reality. It can be done in two-step process. First, the position of the hand in real world is mapped into the hand position in virtual world. This step is usually handled by VR goggles hardware and game engines. As you can see on the pictures, this step preserves character hand's position in relation to the head, because controller's positions are determined relative to the headset position. Next, we have two options for marking final hand position. The position calculated in the previous step can be taken as the final output, or we can perform additional calculations to adjust hand position by applying virtual world restrictions. By virtual world restrictions, I mean constraints, like the presence of the objects in virtual world that are not present in the real world. With such knowledge, our problem statement is to find such final position for the hand that it won't be submerged into the volume of the object present in the virtual environment. Therefore, the hand will stay on the object surface. Our software-based solution applies additional transformation for a hand that is described here as the second step. In current state-of-the-art solutions for determining final hand's position, we have main three approaches. The first one is to ignore all collisions with objects and to let hands go through the object volume. Although in this method the hand movement is unrestricted, the immersion of the application is quite lower, as the hands are not behaving as we know it from the real world. The second known approach is to use default collision solvers from the game engines. In this method, however, we have two issues. In specific cases, we can have non-singular points on our trajectory that will result in discontinuous movement of the hand on the surface. For example, this issue can be seen while sliding on cube edges. This method also can distort greatly the hand trajectory from the expected one, as it uses surface normal to adjust hand position. The third method is to use constraint-based solution. The hand position is taken from the VR hardware, in this video visible as a faint outline, and we have physical hand attached to the real one with a spring-like constraint. In the final application, only the physical hand is displayed. Unfortunately, in this method, hand happened to jam in the local minimum or maximum of the surface, as it can be seen in the video on the bunny's legs. All things considered, we propose our solution that address this problem and mitigate drawbacks that are present in other existing methods. In our solution, we propose a method that uses a vector field for calculating the direction of the hand projection onto the object's surface. In our approach, we intended to create an easy and intuitive method so that those vector fields could be set up by designers without any prior knowledge. And lastly, we aim to implement our solution as plug-and-play module in Unreal Engine. Such three example vector fields defining projection direction are shown in the pictures here. The first two can be generally visualized as a plane, the third one as a sphere, and because of that we created a method using visual representation of the projection shapes. The projection shapes are helper shapes that are set up in the vicinity of the object, just as the colliders are usually set up around the mesh. In this video we present three projection shapes, displayed in red color: plane, sphere, and cylinder. Any projection shape can be set up for any mesh in order to customize the experience of specific hand movement on the object surface. The three projection shapes differ in the output vector field they produce. The virtual plane creates projection direction based on the plane normal vector. The projection direction for the virtual sphere is calculated from the sphere center to the hand position. For the virtual cylinder, the hand projection direction is calculated from the cylinder axis to the hand position. With a correct projection shape being set up for the glided object, we can define smoother and nicer movement of the hand for the user. We compared our solution with the state-of-the-art solutions to check our method for both precision and the speed of the user's movement, as well as the user experience. Here we present two state-of-the-art approaches, without any collision and a constraint-based one. Please note that in those videos we allowed for the free user's hand movement, and we didn't intend to follow the orange line. The no-collision method allows for the hand to submerge into the object. While this is the most popular method used in VR applications, it can break the immersion of the user's experience. In the constraint-based method, we can see that the hand is stopped in local maximum and later is quickly pulled to concur with real hand position. This method fulfills a requirement of the hand staying on the object surface. However, produced hand movement is not smooth as it has non-constant velocity. In our method, the hand movement over the object is smooth, even on the cube's edge. The virtual plane position for this test is perpendicular to user's view vector, and such plane orientation had the best overall experience in later tests. Using virtual sphere over the cube's shape for projection allows user to have smooth motion not only on the edge, but also over the corner of the cube without any special projection shape positioning. Hand guiding with virtual sphere slightly distorts horizontal and vertical movement, so it feels as if the user is gliding over a sphere, not a cube. The cylinder shape was placed here vertically. Using virtual cylinder as the projection shape is the hybrid method between virtual sphere and virtual plane. In horizontal movement, the hand behaves like with the virtual sphere, and in vertical movement, it feels like using virtual plane. We tested our method against constraint-based state-of-the-art method. The constraint-based method created non-smooth movement, which was hard to control, while the movement using virtual plane guiding was smooth and precise. In the test against cube's edge, both methods were precise. However, in constraint-based method, the velocity was not constant, which resulted in sudden jump of the hand after passing the edge. In our method, hand slided without any stop. To check our method, we decided to design multiple test cases and modes, and for that purpose we prepared a large testing module. To test our method, we prepared 3 basic test scenes. First was the sphere, to test non-planar movement over curved object. Second was the cube, to test movement over the edges and corners. And third was the plane with the spheres. This scene was designed to test our method for a mesh that resembles control panel with 3D protrusive elements or cockpit of a plane. Each scene consisted of 1 up to 3 test trajectories of a chosen regions that were particularly difficult while using market VR applications. To test all methods and find which was overall the best, we tested 5 mapping methods, 3 our own projection shapes, that is, virtual plane, virtual sphere, and virtual cylinder, and 2 state-of-the-art methods, that is, no collision and constraint-based. On top of that, we had 4 test modes, either static or dynamic, with the follow trajectory being switched on or off. Summing that up, we had 5 trajectories, 5 mapping methods, and 4 test modes, which produced hundreds of unique test configurations. Each of the test configuration was repeated about 5 times, giving circa 500 tests performed by each of 14 participants. Each participant spent about 1 to 2 hours to complete the required number of the tests. Here we present the results of the tests. We aimed for the value of 4, as this was the radius of the sphere that was the visual representation of the user's hand, and this was the requirement for a hand to slide over the surface. The last result here, NC, stands for no collision, and it is the only test that differs greatly from the other results. The non-collision method proved to submerge into the volume, as the users were unable to stay on the object's surface. Other results, that is, free projection shapes and constraint-based method, were quite similar. The only thing I want to notice here is that those results present the distribution of the distances, and because of that, they don't show the non-smooth movement of the user's hand in constraint-based method. To check the moments where the user's hand is getting stuck in local minima or maxima in constraint-based method, we plotted the position time graph for a test with a dynamic test mode. In this test mode, hand had to follow a ball on a trajectory. The ball moved with a constant speed. The local jamming of the hand is easily seen on the graphs here. Last but not least, we checked the algorithm performance. To be usable, the hand adjustment method using the projection shapes cannot slow down application below acceptable for VR minimum. In order to measure our method performance and its overhead, we conducted experiments for 3 complex models: the Stanford Bunny, a scanned heart originally in high resolution, and modeled cockpit mesh. Each of them was generated in 3 different LODs, one low poly with about 5,000 of triangles, mid poly with about 40,000 of triangles, and high poly with about 400,000 triangles. The performance was tested on the machine with NVIDIA GeForce RTX 3070 laptop graphics card, Intel Core i7 10th generation, and 32 GB of RAM. We used Oculus Quest 2 goggles as our tested VR headset. The results for all methods, both state-of-the-art non-collision and constraint-based, as well as our projection shapes methods, oscillated around 72 frames per second. It is worth noticing that Oculus Quest 2 has 72 Hz frame rate cap, so the performance of the application was limited only by the used headset. Our proposed method proved to improve user experience, as well as the precision and the speed of the user's hand movement over the surface of the objects. Our method is a proof of concept that can be further explored. Thanks to method's visual representation as the projection shapes, it is easy and intuitive to set up the desired projection method in Game Designer. There are, however, potential improvements that can be tried as a future work. First of the ideas is automatic selection of the best projection shape for each object. Another improvement is automatic switching between different projection shapes within one object. We can also imagine creating additional projection shapes like capsules or even complex shapes, being smooth approximation of the surface. And for existing projection shapes, we can explore further, dynamically changing the properties of the projection shapes during the runtime, depending, for example, on the user's view direction. That's all for our current research. Thank you for listening, and if you have any questions, I'll be more than happy to answer.
Questions? All right. There's a microphone next to you.
So I wanted to ask about, obviously at the end, like the limitation of just being limited to 3 primitives. I want to ask about if you had any possible solutions for having maybe either user-generated or automatically generated vector fields. I know there's like a metaball formula for automatically generating vector fields. I was just wondering if you had considered that, like for more advanced objects, you wouldn't just be limited to primitives.
Yes, that's a very good question, and this is what I meant by adding additional projection shapes. So, for example, the smooth approximation of the surface. If we would be able to generate any vector field, it would be really good because either designers wouldn't have to set it up, or in the different case where they have to set it up still. In that case, the visual representation of such projection shape would be might be problematic and not intuitive for the designer. So in that case, we considered this, of course. We still didn't pursue this path, but this would require either to turn off this possibility for the designers to set up a projection shape for each object, or to come up with setting the nice visual way to show to the designers how to do this. Yes, but that the smooth approximation of the object would possibly be enough to create the smooth motion on the surface.
Okay. Thank you.
Okay. I have 2 questions. First off, when you said like use a Quest 2 at 72 frames per second, did you choose to cap it at that, or is that like pretty much what it could possibly do?
Did we use
like as you said, like when you're running like your test, you had the Quest 2 at 72 frames per second. Is that just, and you got like an average of about that? Was that like, did you cap it at 72 frames per second, or could it go higher than 72 frames per second?
The goggles, the Quest 2, in the specification have this cap, frame rate cap. So we just used the goggles, and out of the box we had this frame rate cap. However, we used the Unreal Engine profiler so that the number of the frame rates, as you can see, it was oscillating around 72. So sometimes it tended to be a little bit higher, but that's just only because of the Unreal's Engine output that they showed in the profiling tools.
Okay. In the developer settings for like the Quest, you could set higher than 72. You could set to I think 120 through the developer settings for the hardware.
We didn't test that. The higher frame rate setting. Of course, we will do that as soon as we will be able to unlock this, or either use a different set of goggles.
Okay. And like the second question is that, can you run multiple of these projections at once to create like simulate like the fingers on hand? Let's say you would have one for each finger, and you would have like maybe like a multiple like a more complex shape.
For now, we're not using the projection shape for each finger. Instead, we are using projection shapes for each object. So it's not user-based, but the object-based. So for one hand, we can choose between different projection shapes, but these are defined for each object rather than that. For each finger, of course, they could be different, but still, first thing that we would have to solve would be this automatic switching between different projection shapes, and what goes after that, we would have to be able to switch between different vector fields.
All right, that's all the time we have, unfortunately, for the questions. But thank you. That was wonderful.
Thank you.
Okay, our next paper is entitled Generalized Dynamic Multi-Agent Torso Crowds.
Good afternoon, everyone. This is Vilas Talukdar from New Jersey Institute of Technology. My today's topic is Generalized Dynamics Multi-Agent Torso Crowds, and my co-author is my PhD advisor, Tomer Weiss. So as you can see, like, there are hundreds of people and they're making individual navigation decisions in every second. That makes overall dynamics very complicated. So our goal is to like simulate this virtual these dynamics virtually. And this multi-agent dynamics has typically applications in movies, games, animations, where we want to create large virtual crowds. Also in robotics for making the robotic navigation smoother, and also in emergency evacuation of large buildings, stadiums, and pedestrian safety analysis. But my main focus of today's talk is a subdomain of multi-agent dynamics, which is like modeling intrinsic crowd behaviors. For example, rotation, sidestepping, and interaction, which are usually seen in pedestrian dynamics in normal walking or in any other common places. So in this paper by Ludwig Hoyt and his colleagues, they discuss the importance of body and shoulder movement while moving in a common space, where in the left side they are showing a single person is crossing a crowd flow without shoulder motion, on the right side with shoulder motion. And we can see that the right side is visually more plausible compared to the left one with the shoulder motion. But they add shoulder movement at the animation level, where our focus is on like incorporating this shoulder motion during the collision avoidance. So now I will discuss like most prominent approach to represent crowds in crowd simulation, which is disk-based representation. So in disk-based representation, usually crowd are like represented as 2D disk, but though like these are mostly common and very good in simulating crowds, but they have some limitations. For example, they overestimate the human's ground profile. So if we represent our like torso profile as with a disk, we are kind of overestimating some spaces in front and back of us. And another limitation for the rotational symmetry of disk, you cannot naturally like incorporate rotation and twisting, etc. For example, this is one of the disk-based crowd simulation by Thomas Wise. We can see there is absence of like rotation, which could add like more visual fidelity if there was any rotation to avoid the collisions. But there are some solutions of these limitations of disk-based crowd simulation. For example, in some approaches, it is forced that the disk or the crowd need to always face it direction of velocity, but they cannot respond to like orientation dependent local interaction. For example, if the disk-based crowd need to rotate or twist in between these narrow walls, they cannot do it. So before going like too deep in the topic, I will show some of the results of our method. For example, this one, where we can see thousands of people kind of facing each other and moving from opposite side, and there is rotation and kind of twisting in case the narrow spaces to pass through each other. And in this example also, one single crowd is kind of tasked to pass a crowd flow where the shoulder rotation twisting helps him to do this. Now, like I will discuss some of the most significant related work which are non-disk based. The first one is by Stubel and his colleagues. So they represent crowds as capsules, and this is a clearance driven body rotation, like the rotation will be based on available clearance, and they divide the entire crowds as active and passive agents, where active agents kind of navigate and passive agents kind of need, like passive agents just have a very minimal movement to like allow the active agents to pass the goal, and they use the Bernoulli diagram for the path selection. This is one of the examples of their method, where you can see active agents are kind of entering in an elevator and passive agents just have minimal movement kind of rotation or something. And once the active agent reaches the goal, their like rule become as a passive agent. So there's some limitations, as for example, they are very limited. They have very limited applications in the scenarios like elevator and other dense scenarios. So they are not generalizable across multiple scenarios with multiple densities. And also their dividing rule of active and passive agents limits the real-time dynamic behavior of the crowd. This is another work by Narang and his colleague, where they present crowds as elliptical shapes, and they use pre-computed Minkowski sum table for velocity obstacles. And this is one of the results, where they are kind of rotating their body in bidirectional scenario. But this method has some limitations also. For example, though the ellipses are better than disk, like in approximating the human profile, but they are not as accurate as capsules. Also, they have poor scalability in case of diverse sizes and shapes of crowds. So our motivation is to use the capsule crowds, like we represent crowd profile as capsule, as this is the better approximation of human profile. And our contribution is firstly that we propose a capsule shaped crowd simulation method, which can naturally capture pedestrian rotation and shape, and that can work from like diverse scenarios, starting from very sparse to very dense scenario. Oh, sorry. And another contribution, we propose novel torso collision avoidance constraints, extending the position-based crowd formulation, which can respond to environment spacing. And we don't have any assumption like active agent and passive agent, something like this. So let's see some more results here. So as you can see, two agents are tasked to pass through a narrow wall, and if they continue with the normal orientation, they cannot pass through, they will get stuck. So then they are forced to rotate their body, and as you can see, like they can do successfully do it using our method. In this quad scenario also, like they need to change their orientation to smoothly avoid the collision with each other. So in our approximation of human profile, we represent crowds as capsules, and like to differentiate between our method and traditional force-based and velocity-based approach. So in conventional physics simulation, the velocity and position in next time steps is calculated, and they can like later use the position in next time step to navigate the crowds. So in contrast, we use positional constraints rather than force-based or velocity-based methods. And our method is basically dependent on some scalar constraint function, where we use position-based dynamics PVD constraints, and these constraints are usually equality and non-equality, which control the agent dynamics. So as you can see in the example, there is a cloth simulation example, and a position constraint is basically used. Once the position constraint is dissatisfied, they can correct their position to satisfy the constraint. And these PVD constraints are also applicable in crowd simulation that we are discussing currently. And regarding the velocity planner, we do interpolation between the existing velocity of the current time step and also preferred velocity. So we take a certain portion from the current one and another from the preferred one to like make the velocity consistent in between two time steps. So now I'll discuss some of the novel constraints that we have proposed for capsule shape geometry. The first one, the rotation constraint. So suppose capsule A needs to pass through in between capsule B and C, and there is a very narrow space in between them. So to check whether such navigation is possible or not possible, so we firstly calculate the nearest agent B and C for capsule A. Then in capsule B and C, we find the closest contact points in capsule B and C. So if this is circle, this was a circle, it was very easy. We can like consider only the center points. But in case of capsule, the collision could be in any point like this. So we need to find the closest like point there, which is favorite to contact in between them. So also for capsule A, we compute a point x a prime, which is certain distance ahead of the current time step, to allow the capsule A to rotate its body in case necessary. And once we know these points x, c prime, b prime, and a prime, we can find the scalar amount c1 and c2 to calculate the clearance c. And this clearance basically indicates that how much space available for capsule A to pass through between B and C. And same calculation is applicable for obstacle also. Capsule B and C could be an obstacle instead of a like dynamic crowd. Now, like once we know the available clearance capsule A, we can calculate how much rotation that capsule A needs to do based on the available clearance. So this function determines the amount of rotation that capsule A needs to do. And in case the rotation is necessary, instead of doing it in a single time step, we limit the rotation to a certain certain amount, so that the rotation is not oscillatory. And I remember I mentioned finding the closest point to capsules. Now I will explain in brief how to calculate this. So for capsule I and j, we need to find the closest point xi tilde and xj tilde. And to find this, we can calculate the square distance between these 2 points. And then once we know the square distance, the problem becomes the minimization of the distance d, which is basically solving the linear equation of two unknowns. And we limit the value of unknowns t and s, so that the closest point between line segments. Once we know these closest contact points between two capsules, we can then design additional constraints. For example, the collision avoidance, we can use the constant c mentioned here to determine whether two capsule has already collided or not. And in case such collision is detected, we can use short range collision avoidance to correct the position to resolve the collision. And we also use the personal space constraints, which allow basically a certain threshold distance between two capsules. So in normal pedestrian scenario, each people has some personal space preference around them. So we use a certain threshold distance. And in case any crowd or any person has violated such personal space preference, we can use short range collision avoidance to correct the position and to satisfy the constraint again. Lastly, the long range collision avoidance. This is basically an anticipated collision avoidance. So we anticipate the collision in advance of time, and this is based on a term which is like time to collision. And the lesser the time is to collide in between the agents, the larger the avoidance behavior is. And in case we detect some such future collisions between two capsules, we do short range collision avoidance to resolve such future collision in advance of time. For example, let's see some some of the results of the long range collision avoidance. We can see that the agent's motion is anticipatory, and the avoidance is larger when they are closer to each other. Here also, we see in passing orthogonal and circumference scenario, agent can anticipate the future collision with each other and do resolve such collision in advance of time. And regarding the comparison, we do compare our results with one Diggs-based PVT method on the top right corner and two other elliptical crowds. We can see that our method on top left corner can anticipate the available clearance in front of them, and they can do necessary rotation to avoid each other in between very narrow walls. And this is the single agent scenario. And in terms of other two elliptical crowds, the rotation and avoidance is not as smooth as ours. We also compared in bidirectional scenario with the elliptical crowd, where the result is visually similar with elliptical crowds. In both methods, agents are rotating in case it is necessary in front of their narrow space. And we also compare our result with capsule crowds mentioned in related work by Stubel, where we do like replicate the similar active agent passive agent behavior using our method, and active agent kind of moves navigate from start to end position, and passive agents are kind of having very minimal rotation and movement to avail the clearance for the active agents. So this is similar behavior we saw in the capsule crowd paper by Stubel. And like we also compare our method with some ground truth data, where we can see that on the right side a real world escaping video. So our method can simulate such scenario with the rotation and like velocity variation. We can see that our agent can anticipate congestion in front of it and can like reduce its velocity and accelerate once there is available clearance in front of them, which is similar to the real world phenomena. And regarding the like metrics, we compare our method with the ground truth experiment, where two agents needs to pass through the narrow wall, and we do compare the travel time and rotation with respect to the available corridor width. So as the corridor width reduces, the rotation is increasing. So we compared the similar experiment that mentioned on the real world crowd. But we do it virtually, and we can see that the change of travel time and rotation is similar to the real world data that reported in the paper. And regarding other metrics, the collision avoidance and navigation time is lesser in our method compared to the disk-based PVD, and we saw anticipatory collision avoidance in our method. And regarding performance, we had like lesser FPS compared to some of the scenarios of capsule crowd paper by Stubel. And we implemented our method using JavaScript, and for rendering we used Unity. We have some limitations. Currently we have homogeneous crowd with same capsule length and speed, so probably like making it varied capsule length and varied speed could help us to make the crowd movement homogeneous. And also our rotational planner is based on available clearance. Currently we don't consider different real world factors, suppose following behaviors, crowd density, etc. And currently our velocity planner is simply goal driven, which help the crowd to navigate from the starting to goal position regardless the external environment. For future direction, we can incorporate other important notation of pedestrian dynamics like psychological factors and group dynamics, which will add more fidelity in the crowd motion. And also like incorporating of more detailed human body model and animation will increase the overall fidelity of our result. Finally, adding GP-based parallelism would help us to simulate even larger crowds, probably few thousands of crowds. So currently we do it with thousands of crowds. In summary, we propose a constraint-based approach for simulating capsule-shaped crowds, and our crowd can exhibit plausible navigation behavior that's seen in the real-world crowds, like rotation and twisting. And like our method is stable with larger time steps. These are the references. Thank you. Feel free to
Thank you. Are there questions from the crowd? No? Anyone? Yes. All right, we're going to bring you a microphone.
Were you, with your method, did you identify any like unique failure modes that previous methods didn't have? Like any like pedestrians getting in cycles or something like that, or stopping?
Could you please repeat the questions?
Sorry.
Could you repeat the question?
Yeah, did your method have any failure modes that other previous methods didn't have? Like pedestrians getting stuck or something like that.
Do we have any failure?
Yeah.
Currently, I don't remember that we can't. Probably if we can incorporate the learning based method like limited reinforcement learning or something that could add more random behavior compared to the current traditional crowd simulation method. So that I can there has been already advanced in learning based method. So probably incorporating learning based method with capsule shape could produce more dynamic and nice behaviors.
Thank you.
Can the dimensions of the capsule be adjusted on a spectrum between just perfect disk and like line, and can that be optimized for the best behavior? I'm sorry if you already went over that.
Could be. Can you?
So like say on one end is perfect disk, on another end is really long capsule approaching a line. Can you adjust that and have it be set to the optimal for the behavior that you want?
So it's about incorporating the geometry.
Can you vary between fat people and skinny people?
Yes, that.
That's what we are discussing. We need to incorporate the homogeneous crowd behavior. So currently, heterogeneous crowd behavior. So currently it is homogeneous. They can detect the same shape of crowd, but if you want to make it varied shape of crowd, it's possible. That is it's the matter of changing some representation and equations. Probably.
I think he said that was future work toward the end.
So do you think there's any potential to turn this into an interactive tool where the user, let's say they're in Unity, could adjust sliders like how panicked is the crowd, how urgent does this person need to get to their goal, just different parameters with the crowd, and what actual mathematical sliders could you adjust to change things like crowd panic?
Yeah, it's a very good question. So as if I understand your questions correctly, so you are referring to certain interacting UI that you can play with the parameters, and accordingly the crowd behavior will be changed, right? Correct? Okay. So yeah, that we were actually discussing in our research group. So there is basically such UI available for images. I forgot the exact name. So we were planning to design such JavaScript UIs so that playing the parameters could you can play the parameters and generate diverse kind of behaviors. It's possible, but we haven't explored yet. Yeah.
Time for one more question.
Yeah. It's more of a little more of an AI question than a graphics question, but how similar is this to would it be similar to a flocking algorithm, or if people in the crowd trying to avoid collisions with the person that's coming against them?
Could you please rephrase it? So how is it similar to birds?
To a flocking algorithm.
Could you please rephrase your question?
What I mean by that is that do the agents in the crowd, do they try and avoid collisions?
Mm-hmm.
Yeah, I feel can you adjust the weights of that to make it so they try to avoid collisions?
You mean people are actively trying to stay away from each other more than just not run into each other?
Yeah.
Mm-hmm.
Yeah.
So yeah, it's possible.
Thank you.
Does this satisfy your questions, or we can talk later probably?
Yeah.
Sorry about that. Let's talk later.
Possible, and you'll find out later how it's possible. Yeah. Right. So this paper is being presented online. So first we're going to run the video, and then he's available afterward for questions.
Hello everyone, and thank you for watching this presentation. My name is Bi Han, and I'm a student at the University of Chinese Academy of Sciences. Unfortunately, due to unforeseen institutional policy restrictions and delays in visa processing, I'm unable to attend I3D 2025 in person. However, I'm still excited to share our work with you through this pre-recorded presentation. Today, I'm excited to present our work, titled VMBHINet, which remember by manual hand interaction network for 3D interacting hand mesh recovery from a single RGB image. This research focuses on reconstructing high-quality 3D interacting hand meshes from a single RGB image by leveraging a novel bimanual hand interaction network based on Mamba. Let's dive into the motivation, methodology, experiments, and future work of our approach. 3D interacting hand mesh recovery focuses on accurately reconstructing the 3D mesh models of both hands from input data. This has a wide range of applications in VR, AR, human-computer interaction, gaming, and medical simulations. As you can see in the figure, here are some typical application scenarios where 3D hand interaction reconstruction can make a significant impact. Understanding bimanual hand interactions is essential for realistic 3D pose and shape reconstruction. However, current 3D interacting hand reconstruction methods still have limitations when handling scenes with close hand interactions. They are mainly struggle with occultations, ambiguous appearance, and computational inefficiencies. To address these challenges, we propose a novel approach for 3D interacting hand mesh recovery from a single RGB image that improves reconstruction accuracy in complex interaction scenarios. Our goal is to make significant improvements in both accurately capturing and reconstructing complex hand interactions and enhancing computational efficiency, ensuring high-quality 3D mesh recovery from a single RGB image, and achieving remarkable visual performance in various hand poses. Here we show the visualization results of our bimanual hand mesh reconstruction. The left hand is shown in gray and the right hand in orange, making it easy to distinguish the two. As you can see, our model accurately captures the detailed movements of both hands while maintaining a stable spatial relationship between them, demonstrating strong reconstruction performance. Now, let's take a closer look at the methodology behind our approach. We introduce VMBHINet, the Vision Mamba bimanual hand interaction network, the first framework to integrate state space models into 3D interacting hand mesh reconstruction. This design significantly boosts both accuracy and efficiency. As illustrated, VMBHINet is composed of 5 key components: a backbone network for feature extraction, the VMIFE block for enhanced interaction-aware features, the hand-joint feature extractor for capturing the distinctive features of each hand joint, including its position, rotation, and movement, the joint vision Mamba block for adaptive joint feature refinement, and the dual hand parameter regressor for generating the final hand mesh parameters. Now, let's take a closer look at one of the core components of our framework, the Vision Mamba Interaction Feature Extraction Block, or VMIFE block. As shown in the figure, this model is specifically designed to enhance the extraction and modeling of interaction features between the left and right hands, leveraging the strength of state space modeling. At the heart of VM-IFE block is our innovative VM block, which performs a series of complex convolutional operations and nonlinear transformations on the concatenated bimanual features. Following this, the Interaction Feature Extraction Model IFEM applies a non-local attention mechanism to establish strong correlations between the features of both hands, further enhancing the model's ability to capture the deep interdependencies in bimanual interactions. This collaborative design significantly boosts the accuracy and robustness of interaction modeling in challenging hand pose scenarios. In this slide, we continue by introducing the Joint Vision Member block, JVM block, which is also built upon our core innovation, the VM block. JVM block replaces the traditional self-joint transformer structure commonly used in joint-level attention enhancement models with the more efficient VM block. This substitution significantly reduces the computational complexity and resource consumption typically associated with self-attention mechanisms. At the same time, it fully leverages the strength of state space models in capturing long-range dependencies and dynamic features, making the joint modeling both more effective and efficient. In the following slides, we will provide a detailed overview of VM block and IFEM, highlighting their key contributions to the overall framework and how they enhance the extraction and modeling of hand interaction features. Now, let's dive into the VM block, which serves as the core innovation within both the VM-IFE block and the JVM block in our framework. As illustrated in the figure, this is the architecture of the VM block, built upon the Mamba model. The VM block leverages selective state space modeling for multi-level processing within the global feature space, enabling the effective capture of dynamic bimanual interaction features. This approach significantly enhances the model's ability to understand complex hand interactions, addressing the challenges posed by diverse hand poses and interaction patterns. Let's now take a closer look at the core innovations of the VM block and break down its contributions into three key aspects. First, the VM block leverages selective state space modeling. This design enables adaptive multi-level processing across the global feature space. Unlike traditional models with fixed dynamics, VM block dynamically adjusts to different interaction patterns, which is especially effective in capturing fine, non-stationary hand motions, such as rapid finger movements, while suppressing irrelevant noise. This helps the model focus on what truly matters in bimanual interaction. Second, VM block introduces a powerful fusion of local and global feature extraction. On one hand, local convolutions preserve structural detail, such as palm shape and finger articulation. On the other hand, state space modeling captures long-range dependencies across the two hands. Together, this fusion allows VM block to generate richer, more holistic feature representations, crucial for accurate and robust 3D reconstruction of interacting hands. Third, the design of VM block is highly efficient. Compared to traditional transformer-based models, it removes redundant components like gating units and MLP layers, resulting in a leaner, faster architecture. As shown in the figure, we present the two-stream architecture of the Mamba model, which further simplifies the overall structure. This not only significantly reduces computational overhead, but also makes VM block particularly well suited for real-time applications, such as AR/VR hand interaction systems. In summary, through adaptive dynamics, local global feature fusion, and efficient design, VM block significantly advances our framework's ability to understand and reconstruct complex hand interactions. Next, let's look at the Interaction Feature Extraction Model, or IFEM. Its main goal is to capture how the left and right hands interact. Instead of just using local convolutions, The interaction feature extraction model applies non-local attention, allowing it to understand global relationships between the two hands, even if they are far apart in the image. This is important for modeling complex actions like grasping or manipulating objects, where both hands influence each other. The interaction feature extraction model also handles differences between the hands, such as size or movement, and captures temporal changes to improve dynamic understanding. In short, IFEM helps the model better understanding how hands interact in space and over time, leading to more accurate 3D reconstruction. After the regression of all parameters, the dual-hand parameter regressor takes the predict pose parameters, which capture the hand's movement, and shape parameters, which define the hand's geometry. These parameters are then input into the manual layer, resulting in the generation of the final 3D hand mesh model, as shown in the figure. The final generated 3D two-hand mesh model is saved in OBJ format, making it compatible for loading and use in various rendering engines. For this research, we render and visualize the model within Unity, taking advantage of its powerful capabilities for real-time 3D rendering and interaction. This ensures that the hand model is not only accurate but also seamlessly integrated into interactive applications. This step is essential for achieving precise and realistic 3D hand reconstruction, which is crucial for a wide range of applications, including virtual reality, human-computer interaction, and robotics. The accurate representation of hand dynamics and geometry opens the door to more immersive and intuitive user experience in these fields. This slide introduces the implementation details and evaluation metrics of the experiment. Firstly, regarding the implementation details, we have presented the implementation specifics in the slide. However, we will not go into further details here. Next, we focus on the evaluation metrics, where we use two key evaluation metrics, mean per joint position error (MPJPE) and mean per vertex position error (MPVPE). Mean per joint position error evaluates the error by calculating the Euclidean distance between the predict 3D joint positions and the ground truth. To eliminate the effect of position differences, we perform a translation by aligning the root joint, such as the wrist of both hands. This metric mainly reflects the accuracy of joint location, focusing on the geometric accuracy of the skeletal pose. Mean per vertex position error is used to access the reconstruction accuracy of the 3D mesh vertex positions. Similarly, after aligning the root joint, it computes the Euclidean distance between the predict mesh vertices and the ground truth. Unlike MPJPE, MPVPE provides a more detailed evaluation of the hand surface shape reconstruction quality, reflecting how well the surface shape fits. By jointly considering both joint and vertex errors, MPJPE emphasizes the geometric accuracy of the skeletal pose, while MPVPE reflects the fit of the hand surface shape. Together, these metrics provide a comprehensive, multidimensional quantitative assessment of both the hand pose and shape reconstruction. In this slide, we present the ablation study conducted to verify the effectiveness of our proposed method, VMBHINet. To evaluate the impact of different components on the model's performance, we systematically examine how the inclusion or exclusion of key blocks affects the results. The ablation study clearly demonstrates that the full model, which integrates both VM-IFE block and JVM block, achieves the best performance. It successfully reduces both MPVPE and MPJPE, while also lowering the parameter count and computational complexity. Additionally, the qualitative ablation study results highlight that the full model outperforms versions that exclude certain components, further validating the effectiveness of our approach. This comprehensive analysis reinforces the advantages of integrating these blocks to enhance model performance. After analyzing the ablation study, which emphasizes the significance of different model components. We now present a direct comparison of V and BHINet with state-of-the-art methods in the field. The results, displayed on the left for the Interhand 2.6 million dataset and on the right for HIC, clearly show that V and BHINet delivers competitive performance across various evaluation metrics, including parameter count, G-flops, MPVPE, and MPJPE, showcasing its robust modeling capabilities. This demonstrates the model's strong capabilities and efficiency, further reinforcing its place as a robust solution for 3D hand pose and mesh reconstruction. After discussing the quantitative performance, let's now take a look at the visual comparisons. We present visual comparisons with previous state-of-the-art method, namely InTechHand and EANet, on the Interhand 2.6 million dataset. By comparing the interactive hand models reconstructed from the same monocular image from different angles, we can clearly observe that V and BHINet exhibits a significant advantage in accurately estimating hand poses and interactions. For example, the results highlighted in blue circles in the figure clearly show a better reconstruction of the true positional relationship between the two hands. These visual comparison results further validate the improvements in accuracy and robustness of the proposed method, especially in the application to hand interaction scenarios. We have recorded multiple supplementary videos to demonstrate the real-time performance of our network in dynamic hand interaction scenarios. To conclude, we present V and BHINet, a novel framework for 3D interacting hand mesh recovery, which achieves state-of-the-art accuracy and superior computational efficiency, showing strong and reliable performance across a wide range of complex biomanual interaction settings. However, while the current model shows promising performance, it still faces challenges in robustness, real-time efficiency, cross-domain generalization, and handling multi-hand interactions. Future work could explore lightweight architectures, self-supervised learning, and user feedback to improve performance and broaden the real-world applications of V and BHINet. That concludes my presentation for today. Thank you all for your attention. If you have any questions, I would be happy to answer them.